Hi, in this video, I'm going to go through the OCR AS-level Chemistry paper. This is paper 2, and this is the second half of the paper. Sorry, this is the 2016 paper, and this is the second half, starting at question 5. I covered the earlier questions in another video. Okay, so question 5. Student investigates the reaction between strontium carbonate and dilute nitric acid. The rate of reaction is determined by the loss of mass in the period of time, over a period of time. Explain why there is a loss in mass. Now, unusually, they don't give you the state symbols for this equation. Strontium nitrate is an aqueous solution, and carbon dioxide, of course, is a gas. So you're making carbon dioxide gas. That escapes the flask, and so the mass goes down. That's the answer there. Okay, an excess of strontium carbonate is reacted with this volume of nitric acid. Calculate the mass of strontium carbonate that will react with the nitric acid. Okay, so what can we do? We can work out the moles of nitric acid there. So let's do that. Moles HNO3. We know that's going to be equal to the concentration multiplied by the volume. So you've got 1.25 mole per decimeter cubed multiplied by 20 over 1,000. That's the volume in dm cubed. That is going to give us 0.025 moles. Now we need to look at the equation, see the ratio in which they react. Well, 1 mole of strontium carbonate reacts with 2 moles of nitric acid. So the moles of strontium carbonate that it can react with is going to be half of that. So 0.025 divided by 2, which gives us 0.0125 moles. Now we know the number of moles that will react. We can work out the mass of strontium carbonate. So we need to know the MR of strontium carbonate. Strontium, not one that you sort of remember. The atomic, sorry, the AR of strontium is 87.6. So the MR of strontium carbonate then is going to be equal to 147.6. Okay, so the mass of strontium carbonate is equal to the moles multiplied by the MR, which is 0.0125 multiplied by 147.6. And that gives us 1.845 grams. Right, I would be tempted to leave that just to 3 significant figures because everything's given to 3. It doesn't actually ask us that. So I call that to 3SF. That is going to be 1.85 grams. Okay, the student plots a graph of total mass over here against the time, right? Now, and describe and explain the changes in the rate of reaction during the first 200 seconds of the experiment. Okay, now we've got mass against time, so rate is equal to the strictly speaking, the negative gradient there. Okay, so rate is equal to the negative gradient m, I'll call that there. So we've got to describe what happens during the first 200 seconds, describe and explain, 2 marks there. Okay, so I think we've got 1 mark by saying rate is the negative gradient, and say in the first portion of the graph up to about 100 seconds, the rate of reaction is faster, and after that it slows down. The gradient, you know, around this point it becomes less, rate slows down. Why is the rate slowing down? Well, they've used excess strontium carbonate, so the nitric acid is being used up, and so it's getting more dilute. You've got more dilute nitric acid, you're going to have a slower rate of reaction. Okay, so I'd say all of that for those 2 marks, I think. Okay, now you can probably tell from I've already drawn a tangent there on that gradient. It says use the graph to calculate the rate at 200 seconds. So what you need to do is, like I've drawn there, you need to draw a tangent to the line at 200 seconds. So I've drawn my tangent, I've just rubbed it out. So, okay, draw my tangent there. And we need to calculate the gradient there. So I'll get rid of this. Okay, so gradient is equal to the change in x, so the change in y, which I've incorrectly labeled the change in x there. That's the change in y. Divided by the change in x. Right, the change in y, as you can see there, right, so that's going to be 96.08. And down there is 95.9, so that's going to be equal to delta y. Right, that should be the other way around, really. It should be 96.08. Sorry, notice I was doing the right way around there, so it's going to give us a negative number. 95.8 minus 96.08. That gives us minus 0.18 grams. And the change in x over that same time, delta x, well, that's going to be, that's on 300 seconds exactly, and that's 0. So 300 minus 0, 300. So our gradient then is equal to minus 0.18 divided by 300. That's going to be 6.0 times 10 to the minus 4. And what are the units going to be? They're going to be grams of carbon dioxide, if you like, per second. Okay, that is the rate of reaction at 200 seconds. Right, just to point out there, we've got our gradient is a negative value because, of course, we said earlier that strictly speaking, the rate is equal to the negative gradient. So our rate is a positive number there. Okay, outline a method that could be used to obtain the results that are plotted in the graph. It should include the apparatus required and the procedure for the experiment. Okay, so I would probably do it in a conical flask. And in there we would have our nitric acid and our solid strontium carbonate. You'd probably start the reaction by tipping the strontium carbonate in there. But what I would also do is I'd put a cotton wool bung in there. Obviously you wouldn't put a proper bung in there because it would stop the gas escaping or the bung will pop out. But the cotton wool bung, that will, the reason why for that is it allows the CO2 to escape, but prevents any liquid escaping, any acid escaping, which you wouldn't want that. And sometimes because it's fizzing, you get like a bit of splashing of acid and that can come out of the flask. And because you're not dealing with very big mass losses, that will make a difference. Okay, that whole thing needs to be placed on top of a top pan balance. And you probably want that accurate to this balance, accurate to, well, we'll give readings to 0.01 plus or minus 0.01 gram. And you would need a stop clock, obviously, and you would take mass readings every 30 seconds will probably be adequate. I think they followed it up to 400 seconds. So every 30 seconds up to 400 seconds. Okay, so start the clock when you add the strontium carbonate, put this cotton wool bung in, then that's it. Okay, onto organic question. This is about reactions of butanol. Butanol there. Why is butanol classified as a secondary alcohol? Well, it's because the carbon to which the OH is attached to two other carbons. Okay, so I'll just write that OH carbon attached to two other carbon atoms. Okay, probably going to ask about intermolecular forces because it's given us melting points and boiling points. Right. The shape around the oxygen atom in butanol is non-linear. Predict the bond angle and explain this shape. Okay, so let's look at the bond angle for the. So what we've got carbon here. With don't really worry about this bit. The hydrogens. We have the oxygen there, and we've got an H there. Now oxygen has got always forms two bond pairs and two lone pairs. Okay, and if you drew the oxygen there, well, the three orbitals will arrange themselves to get us, pairs of electrons will arrange themselves to get as far away as possible. Okay, and that means they'll assume basically the orbitals will assume a tetrahedral configuration. Now, the usual tetrahedral bond angle is 109.5, but we're going to get a lot less than that. We're going to get about 104.5. Okay, and we'll just explain this. So what we're going to say is, I think you need to say that all pairs of electrons repel. Because they're all negatively charged. But the repulsion between lone pairs and lone pairs is greater than the repulsion between a bond pair and a lone pair, which in itself is also greater than the repulsion between a bond pair and another bond pair. And that's due to the shape of the lone pairs. They're more bulbous, okay, and that gives us, makes the tetrahedral bond angle, the bond angle reduced from 109.5 to about 104.5. Okay, so you need to say all of that for the 4 marks going. There's 4 marks going for that question. You need to say all of that. Butanol can be oxidized by heating with an oxidizing agent. Write an equation for the reaction and use O to represent the oxidizing agent. Okay, so let's write butanol. Right, so I'll do it displayed formula. Now butanol is a secondary alcohol. So when we oxidize it, we're going to get a ketone. So the ketone we get is going to be butanone. So 4 carbons. We've got, that's a ketone group, and these are all hydrogens. Okay, so we need to balance this equation. Well, we have got 10 H's on the left. We've only got 8 H's on the right. So that means we need to have an H2O molecule coming off there as well. Now let's count up our oxygens. We have got 1 oxygen on the left, but we've got 2 on the right. So that means we're going to need a single oxygen atom with its electrons. That's the oxidizing agent. Okay, so that is our balanced equation there. Okay, a student plans to carry out this oxidation using the apparatus shown in the diagram. Give one reason why the apparatus is not suitable and describe a more suitable way of doing it. Okay, so we've seen before that butanol and butanone are volatile. They've got low boiling points. So if you boiled this for any length of time, you would just lose all of your reactant and product by evaporation. So you need to stop the vapor escaping. So you need to basically heat with reflux, and it's only a 2-mark question, so I don't think you need to, it doesn't ask for a diagram, you don't need to draw a diagram. So you need to heat with reflux. In other words, you have a condenser in the vertical position over a round bottom flask. Again, I'll just draw it, but I really don't think in the mark scheme you have to draw that because there's only 2 marks going. But you're going to have instead of having the beaker, you're going to have a round bottom flask or a pear-shaped flask. There's your butanol with the oxidizing agent. And here you're going to put the condenser vertically like that. No stopper in the top. This is called heating with reflux, of course. There's your condenser. You're going to have the water going in there, the cooling water in there and out there. Okay, so any vapor which boils off is going to condense and drip back down into the round bottom flask. And that's heating with reflux. Okay, this is a yield question. Okay, so 20.20 grams of butanol is reacted with excess sodium bromide and sulfuric acid. I'm going to calculate the percentage yield. So we need to work out the MRs of butanol. So butanol is going to be C4H10O, and the product is going to be C4H9Br. So we work out the MRs of those two. Butanol is 74, and the bromobutane is a lot heavier because of the bromine in it, which is a heavy atom. 136.9 is the MR of that. Okay, so, and this equation shows us that 1 mole of butanol gives us 1 mole of bromobutane. Right. Let's work out our moles of bromobutane. Let's do our moles of butanol first. That's going to be mass over MR, which is 20.2 over 74. That's equal to 0.273 moles. Okay, so we should get that number of moles of bromobutane. So we should get 100% yield. We should get 0.273 moles of bromobutane. So let's work out the mass of that. So the mass of C4H9Br is equal to moles times MR, 0.273 multiplied by 136.9 gives us 37.37 grams. But we don't get as much as that. We only get 25.2 grams. So our percentage yield should be the actual mass over the expected times 100 gives us 0.27. Sorry, use that. We actually get 25.2 grams. We expect this 37.37 times 100. That gives us a value of 67.4%. Okay, now question 7, we have got a big, you look on your paper. I've only snipped the first bit out. It's a 6-marker question, and they're going to give us this percentage composition, and they give us the infrared spectrum, and they give us the mass spec and a little bit more information, and we've got to work out the whole structure. And you get this 6 marks for that. So the first thing we're going to do is work out the molecular formula of the substance, which may be the same as the empirical formula and may not be. We can use the mass spec to help us out there. So let's do the molecular formula first of all. Sorry, the empirical formula. Well, these are percentages, yeah. So in 100 grams, we're going to have 54.4 Right, so I'll write down the like this. So we've got carbon, hydrogen, and oxygen. So the mass we're going to have in 100 grams is going to have 54.5 of carbon, 9.1 grams of hydrogen, and 36.4 grams of oxygen. Okay, so let's work out the moles, which is equal to mass divided by the relative atomic mass, AR. So that's going to be that divided by 12 for carbon, divided by 1 for hydrogen, divided by 16 for oxygen. Okay, so that gives us 4.54. 9.1 of that, and 2.275 of oxygen. So we need to divide by the smallest number to get our ratio, which is of course 2.275, and do that. 9.1 divided by 2.275, that divided by 2.275, that gives us a 2 to 4 to 1 ratio. So the empirical formula is C2H4O. Right, now that may or may not be the molecular formula. It could be a multiple of that. It could be C4H8O2, which I think is actually more likely. So now we need to look at the mass spectrum. Okay, now here's the mass spec. And if we look here to the peak with the biggest MZ value is over there, and that is, I think, at 88. Okay, now we look at the MR of this. If the molecular formula is this, it would be 2 times 12 plus 4 plus 16, which is equal to 44. Okay, so it's not that. That's only half of the value, so you've got to double it. So the molecular formula then, with the MR of 88, is C4H8O2. Now we've got the molecular formula, we can have a look at the infrared spectrum. Okay, all the way, this is all towards getting our 8 marks. And the infrared spectrum should tell us which functional groups are present. Okay, so let's have a look at the infrared spectrum. Right, now I've also pasted in the from the data book. But even before you look at the data, the actual numbers, well, first of all of this stuff is that's all fingerprints. We can forget about that. But this thing here is extremely characteristic of a carboxylic acid. Okay, when you get a broad peak on the left-hand side like that, so if you just see what that is, look, you've got 2,500 to 3,300, very broad. That's the OH from the carboxylic acid. And incidentally, this little side peak, which you always see here, that is due to this CH. That's due to the CHs, and this kind of swallowed up by the very broad OH peak. So there's definitely a carboxylic acid. So write that down as part of your answer. The carboxylic acid, you've got a characteristic absorbance for an OH in that region. And the second thing that tells you you've got a carboxylic acid is the carbonyl carbon of the carboxylic acid. So a carboxylic acid, of course, has got the OH group, which you can detect with infrared, and it's also got that. That's very easy to see where it's that peak there. If you have a look at the chart here, C double bond O, and it's about 16, just over 1600, just over 1800. That's about 1700. So that is almost certainly due to a C double bond O. So you'll probably get a mark for saying that and a mark for the OH. So we know it's a carboxylic acid. So we know we've got this, and we've got 3 other carbons to worry about. So obviously it could be butanoic acid, yeah, or it could have a branch in that chain. It could be methyl propanoic acid. Now they give us a little bit more information here to do with the mass spec. Right, so I've repasted the mass spectrum down there again, and it tells us this bit here. Look, in the mass spectrum, a secondary carbocation is responsible for the peak with the greatest relative intensity. Now, as the peak with the greatest relative intensity is obviously this one here, which has got an MZ of 43. Now, let's just think. The two possibilities we've got, we could have butanoic acid, where we have our 4 carbons. We know we've definitely got a carboxylic acid group, and we've got 4 carbons, so we could have that. The second possibility is we could have methyl propanoic acid, which would be like this. That also fits in. And it couldn't actually be anything else, could it? It could only be those two things. A carboxylic acid with 4 carbons. It's either the butanoic or 2-methyl propanoic. Now, if we look at a fragment here, this could give us a fragment, C3H7, and that would give an MZ of 43. But that fragment would have a positive there. So it wouldn't be a secondary carbocation. That would be a primary carbocation, wouldn't it? That one there. So that's not it. So the secondary carbocation, well, let's see if we lose, let's put the plus on there this time and say that we lose all of that. It breaks, the bond breaks there. Okay, and that would also have an MZ of 43, and it is a secondary carbocation. That's also C3H7. If we look at that, MZ 43. So we can say definitely that our structure is not butanoic acid, it is 2-methyl group on there. Don't actually need to call it 2-methyl, just methyl propanoic acid, that will do. That's what we've got. And that is the last question on the paper.